Okay, welcome back again for the final talk in the second day of panel presentations in astronomical observational techniques and instrumentation. The next talk is by Tanmayee Gupte, who's going to be talking about edge-on late type lens galaxies.
Hi, I am Tanmayee Gupte, and I'll be talking on edge-on late type galaxies. I know the title is kind of vague, but as we go through the presentation, I will be able to tell you why I'm being so specific about this type of galaxy. Okay, so this is the outline of my presentation. I will be presenting the science question first, which is like very important, and the background it is required to answer my science question. Then I'm going to tell you about the object, like which object I'm analyzing, and the observation part, which telescope I'm using and what frequency and what kind of telescope it is. Then the analysis, and why is this important? Because it answers, so it's just not about answering the science question. There's a lot of future implication to why we are studying this kind of particular galaxy, and future work, because you need to do more work on answering the later on science question. So my science question is, what is the mass of the H1 gas in galaxy 1703245? I know, again, it's vague, but as we go through the presentation, you'll come to know more about it. So the background, okay. So, there are many different types of galaxies, and mostly I'm going to discuss about spirals and elliptical galaxies. So these E2 and E4, these are the elliptical galaxies, and the S is our spiral galaxies, and SV is barred spirals. You can see the barred structure in them. So in elliptical galaxies, so they have an ellipsoidal structure, so the intensity brightness makes the elliptical kind of structure, and they have the stars are red color, which is that relatively cold stars, and so there is no gas, there is no H1 gas in them, so there is no star forming region, and they are called as the old galaxies because there is a theory that elliptical galaxies are formed after merger of two galaxies. So that is if you believe in galaxy mergers. And as for spirals, they have spiral structure. You can see the spiral arms. They contain hot blue stars in the disk, and that is because they have a lot of gas, H1 gas. That is a lot of star forming region, and they are said to be young, like recently formed galaxy structures. And this is a face-on spiral galaxy, and this one in particular, this is an edge-on spiral galaxy. So the edge-on, which was there in my title slide. So I'm studying a galaxy which is like this. Okay, so my object was a part of SWELL's survey. So SWELL's is slow in WFC, that is wide field camera, edge-on late type survey. So late type galaxies are spiral galaxies, and there were a large spectroscopically selected sample of edge-on late type lens galaxies, and they have my object particularly is at a very low redshift, which is important because if you have a gravitational lensing system, then that object is at really high redshift because you need that much of optical depth for the gravitational lensing to happen, and you can see visible signs of interaction, that is probable substructure, which is like you have a parent galaxy and then you have a dwarf galaxy, and they tidally interact with each other. So there are probable signs of this kind of tidal interaction in the galaxy, in the object that I'm studying, and it is a gravitational lensing system. So these are the SWELL's galaxies, the survey that happened. As you can see, they are all edge-on type of galaxies, and this is the galaxy that I have analyzed. And you can see that there in the brackets, you can see there is A, there is C, and X. X and B. So A is the galaxy system is a gravitational lensing system. Like we can say with really high probability that yes, it is a lensing system. So B, C, and X. So as we go through that, the probability decreases. So for X, you can say it's not a lensing system. So, like I said, what is so special about these galaxies? The distance, they are at really, so the distance, gravitational lensing, and spiral structure. And this kind of galaxy will help us to constrain the dark matter distribution. So the distance is approximately 0.1 redshift, which is like very nearby. And so it is the closest sample of gravitationally lensing spiral structure. So gravitational lensing. So what is gravitational lensing? So this is us over here, and this is the deflector galaxy, and this is the source galaxy. So because of this bending of space-time curvature, the light that is coming from this source galaxy will bend around this deflector galaxy, and we'll be seeing a sort of an arc of this source galaxy. Or like, you know, if you see a complete arc, it is called as the Einstein's ring, and since because of the bending of the light. So this is the gravitational lensing system, spiral structure. So now why do these galaxies have to be spiral structure? Why can't they be elliptical galaxies? Because spiral galaxies, like I said, are young and have star forming region. What does this mean? This means they contain H1 gas, and this is very important, the H1 gas, to constrain the dark matter substructure. Because when you do analysis of the H1 maps, you're able to tell if you're able to constrain the dark matter substructure. That is, if there is a dwarf galaxy nearby having dark matter in it. And also the dark matter density in the parent galaxy also. So my object is this one, 17032451, and these are the RE deck of that galaxy, and it is at a redshift of 0.063, so it is really low redshift. Okay, so this is the gravitational lensing. So in the paper, the Swells paper, so what they did was they made a model of the deflector galaxy, and they subtracted it in different bands, and you can see in the K band there is this arc which is formed, which tells us that it is a gravitational lensing system. And so there is this arc, and then there is this small arc over here also. So it's not a complete Einstein ring, but you can see a feature of gravitational lensing system. Observations. So the observations, so on this project currently one of our senior students, Andrew Lipnicki, is working on it right now, and he took observations from the Green Bank telescope, which is a telescope of 100-meter diameter, and the operating range is from 0.1 to 116 gigahertz, that is meter to millimeter, and the expected signal, so we expected the signal at 1.39 millijanskis, so a resolution of 0.278 millijansky was was asked kind of for the telescope to get, so that we get a signal to noise ratio of 5, that is a 5 sigma. If there is a detection, then we can get a 5 sigma detection. And the reason why this single dish telescope is used, and we did not go for big telescopes like VLA or interferometer telescope, is because, so you have this galaxy that you're studying, and this single dish telescope will be able to get the spectrum of the entire galaxy. But if you go for VLA or interferometer telescopes, then it will study little parts of that galaxy. So that kind of will over-resolve the galaxy that we are studying. So currently we just want to know how much H1 gas is present in the galaxy. So for which Green Band telescope was the perfect telescope to study it from. So this is the spectrum, this is the on spectrum, which is the spectrum of just the galaxy, and this is counts and this is the frequency. This is the off spectrum, which is the spectrum of the sky without the galaxy. So after the galaxy moves through the during the daytime or the nighttime, whenever the observations are being taken, this spectrum was taken from the same region where the on spectrum was taken, so that there is not much changes in the sky that we are studying, in the background sky that we are studying. Analysis part. So I use the software GBT Ideal, which is ideal software particularly for GBT, and I did position switch, which is I have the on spectrum and I have the off spectrum. So I subtracted the off spectrum from the on spectrum. Then I fitted a polynomial of order 3 and subtracted it as the baseline. And I did boxcar smoothing to get a velocity resolution of 100 km per second from 80 meter per second. So the reason why I did this was getting velocity resolution of 80 meter per second is very high. We don't need that high velocity resolution. So after doing boxcar smoothing, the velocity resolution became 100 km per second. This reduces the amount of time that we need to take the observations for. That's why we do boxcar smoothing, and then I averaged 34 observations of 4 minutes each, and integrating after they are integrated over 1 second. So this is my final spectrum, and this is the galaxy, and you can see there's a lot of noise. It's because this is in the radio frequency, so you get a lot of interference from aeroplanes, but since this is not even half of the data that we have collected for this project, more data is getting collected even now. So after doing even analysis of even that data also, we expect that majority of the noise that you can see over here will be gone. And this is a 3 sigma detection. So this is the galaxy that we expected this galaxy. So we can see that this is the galaxy is because we expected the galaxy to be at this frequency, and like I said, the 1.36 millijansky was the antenna temperature that was expected. So we do get a bump over there, which is pretty significant. So you can say there is a probability that it is the galaxy that we're seeing over here. So mass of the galaxy, I calculated the mass of the galaxy using this formula, where this is my signal, this is the velocity resolution, and I get the mass of H1 to be 1.7, 10 to the power 9 solar masses. Now from the, so this is the mass of H1 gas in the galaxy. So why, like I said, why is this important? So now, extended H1 disks are ideal tracers for tidal interactions with satellite galaxies. So you have a parent galaxy, and there is H1 gas in it, and the H1 gas is extended to more than the optical radius of the galaxy. So if there is a dwarf galaxy nearby, the tidal interactions between the parent galaxy and the dwarf galaxy can be seen if we study the H1 map of the parent galaxy. And we can infer the mass and relative position of the galactic satellites from analysis of observed disturbances in the outer H1 disks. And this can be used to constrain the density profile in the primary galaxy, the density profile of dark matter in the primary galaxy. And this method is complementary to the gravitational lensing method in probing the cold dark matter substructure and the dark matter distribution. So, like I said, why is it important that these galaxies are gravitational lensing system? Is because with the gravitational lensing system, you can get another way of constraining the dark matter. So you can compare both of these methods and see if the answer from either of these two methods, if they match with each other, then we get a pretty good idea of what kind of dark matter distribution is there at galactic scale. galactic and subgalactic scale. So, you know that the cold dark matter, so after observing the rotational curves of galaxy, we know that the cold dark matter structure or cold dark matter was at really large scales. We are able to see evidence of dark matter, but for galactic and subgalactic scales, we still are facing problems like the missing satellite problem. So this method will give us the dark matter distribution at galactic and subgalactic scale. So that's why it is really important to study these galaxies. And after getting the mass of this galaxy, so we know that the mass is high enough that the high resolution maps of H1 gas in this galaxy will give us the dark matter distribution. So high resolution maps of H1 gas in galaxies are required to constrain dark matter distribution, and obtaining the H1 masses is the first step in determining which sources are optimal for follow-up. Like, should we invest more time in the really, expensive telescopes like VLA? Because if the mass is not high enough for the H1 mass, if it's not high enough, then we will over-resolve the galaxy and thus waste a lot of time of a really expensive telescope like the VLA. So the future work is analyzing all the data from the GPT observations that is getting collected right now, even now, and confirming that the mass of galaxy is how much we had expected, and if it is enough to actually get high resolution map of H1 gas, then after confirming that it is enough to get a high resolution of H1 map, getting actually the high resolution H1 maps of the galaxy using VLA, and then when you compare it with the simulations of CDM, like the tidal interaction, we will be able to constrain the CDM substructure at galactic scales, and thus getting a proof of CDM model at galactic and subgalactic scales. So, yay, dark matter. And thank you. I would really like to thank Andrew for helping me through this project because I kept bothering him. And yes, that's it. Thank you very much.
Okay, we have plenty of time for questions.
Can you go back to the slide with the spectrum, please? The plane spectrum. Yeah. Yeah. So the place where, sorry, because I'm sitting kind of far, so I can't exactly see it. The place where you said you detect the galaxies, do you mean by you detect the emission of the H1?
Sorry?
Where you point to like
Yeah.
the galaxies, do you mean that's the emission line?
Yeah,
from the
H1. Yeah.
Okay.
So it's redshifted, right? So it won't get it at 1420. So that's why.
Oh yeah, I just had to confirm this one.
Yes.
Can you go back to, I think it was 15 or 16 slide where you had the residues from the model subtraction?
This one?
Yeah, this one. Okay, so in the last one, in the K band where you see that you have the little arc there, can you see that in the original image by any scaling factor? And like the first row, are those the
This is the
actual,
original image.
those are the
yeah.
original
Yeah.
images, okay, okay.
So that's the dash.
So,
okay.
It's also
Yeah, that's how
It
different
zoomed
scales
in
well.
Oh,
So
yeah, that's right. Gotcha. Okay, so that will correspond to pretty much the inner, okay, that makes sense.
Yep, she.
Never mind, I think she answered the one in the slide.
Okay, more questions?
How do you get that mass of H1? You dropped a formula on us out of nowhere. Where does that come from? And wait, you don't have to tell me. Yeah, you don't have to tell me. You know, like the paper, and just like roughly why this formula?
I really don't know.
Okay. Yeah, that's fine.
So then presumably this is, What's the, oh, D is the distance, so this is the volume emissivity of 21 centimeter, I guess, integrated over the volume.
Oh, okay.
Yeah, would have been interesting to see a derivation because it's probably straightforward. That was my question, is how did you get this formula? But you got it by writing it down. Right? And my other question was, is this a 21 centimeter line? Somehow I didn't know that. So that's what, it's 1440 megahertz, is
Yeah.
that right?
Yeah.
1420.
That's a 21 centimeter line, right?
That's
Yeah.
2020.
Okay. I have some other questions. How do they pick the galaxies in the swells sample? You showed us a montage. Are those all the galaxies in the swells sample? And were they chosen to be edge-on at the same distance?
Yes. No, not at the same distance. They were chosen to be edge-on spiral structures, and this one.
Yeah, are those all the galaxies in the swells sample?
Yeah.
And-
I think there are a few more of them, but there are.
And why were they chosen? I'm just curious.
Why are these ones chosen?
Yeah.
Because they were, like I said, edge-on and spiral structure also. And the way they chose this was if there was some kind of like gravitational lensing probability of it happening, like in that 4x4 window, if there was some kind of structure that is seen after at different wavelengths or different frequencies, then they chose those kind of galaxies. Like when you take the spectrum of one individual galaxy, because of the lensing system, like the source, you'll get another spike at that frequency, right? So that was another method by which they chose these galaxies.
Okay, and then you said the expected signal was 1.5 millijansky or whatever it was.
1.39.
1.3. When you say expected, who expected that? And why did they expect it?
So you can get the mass, you can get the probable mass of the galaxy from NUVR color map.
Oh, so based on someone's notion of what the
Yeah.
mass might be,
Yeah.
then you can, an expected content of H1, then you could integrate the emissivity of H1 over that volume, and you might expect 1.3. On 22, could you go to 22? You said a few things about noise.
Yep.
Yeah, I thought at one point you said something about the SNR being 3.
3 sigma.
So can you point at the noise in that plot?
So it was just since it is an initial stage, we just took the average of the bumps over here, considering.
So I would have thought that the noise, without knowing what's real, because you have to know what's real in order to know what the noise is, but I would have thought that this is the noise.
Yeah, that is
And to me, this is much more than 3 times this. But
but
if
you
you tell
have-
me these are the noise, then maybe I can understand
Yeah.
where the average noise is 1/3 the
So they took
equivalent.
the average of all the bumps, the noisy bumps, and they took
So
that as-
these are noise bumps?
Yeah,
Is this a noise bump?
no,
How do you know?
because we expected a signal at that.
Let's go.
Be interesting to follow your career, okay? We expected a line there, so that one's real, interesting.
I mean, I know it's still, but with more data will give us more, higher detection.
Can you go to 23? I think that's the, oh yeah, how is that derived? Okay. Any other questions? Yeah.
Can you go back to the spectrum again, please? So is the negative voice comes from subtracting the sky? Like how do you decide the zero point, at the zero level on spectrum? Because you have some negative values. Could there be like emission line in the atmosphere or something? Oh, sorry, absorption line in the atmosphere or something?
Maybe.
I mean, it's worth checking.
I mean, because it's subtracting the sky, right, some of that might go into the negative, so.
Which is why I was asking whether that's like the assumption or something in the sky.
Actually, what's the, I don't know this, what's the y-axis even? It says antenna
Oh,
temperature, what
that's-
does that mean?
That's how regular.
Power
That's
sound.
how regular.
It's annoying, isn't it?
I have no dogs in this fight, so.
It's the temperature of a resistor that would have Johnson noise equivalent to that signal, which probably doesn't help you.
I know.
Unless you
I know.
carry magic resistors in your pocket at different temperatures.
You have to teach them all different terminologies.
Yeah, well, it's,
Cool.
so antenna temperature's used, right? It's, so anyway, any other questions? No, okay.